Good morning, everyone. We'll be starting soon. Recording. Good morning to all of you. We'll start off with R today, an introduction to R, and then we will proceed with other things. So we'll do a small example using R to do some statistics as well. But it is essential since most people said that they were new to R, they have never used it. So some basics are essential. And here we go. So R, an introduction. What is R? R is a free software environment for statistical computing and graphics. R is a programming language and the environment commonly used in statistical computations, data analytics, and scientific research. So a lot of researchers, they are using R. It's getting very popular. And the reasons for that is R is compatible and runs on a variety of platforms. It runs on Unix, runs on Linux, Windows, and Mac. Other reasons why R is popular is R, apart from being very powerful, which can do a lot of statistics and graphical work. It does things like linear and nonlinear modeling. It handles classical statistical very well. It does time series analysis, classification, clustering, almost everything you require in statistics is here. And over and above, R is an open source software and it is free. There are other alternatives to R. For example, we have SPSS, but this is very commonly used by social science people. Not that it can't be used for sciences, it can be. You have SAS, statistical analysis system. A lot of it is being used in corporate world. But the downside of SPSS and SAS are they are both proprietary software and they cost a lot. SPSS can be downloaded and used for 20 days freely. But after 20 days, you'll either have to buy or install it on some other system. You can't reinstall it, uninstall and reinstall on the same machine. Then Python is also coming up very strongly, and a lot of people who have been using R are migrating to Python, or they are using a mixture of both. And R routines can also be called from Python, which we shall see later as we proceed ahead. So Python, again, as we all know, is an open source and free software and very powerful. So, yeah. So I hope all of you have installed R. Can you please put on chat window whether anyone has had a problem or have most of you installed R? Yeah, so some have said installed successfully, installed, very good. So, yeah, irrespective of which operating system you are using, Linux or Windows or Mac, I'm sure you know now how to invoke it. And in Windows, you can go to the start button right below, and the moment you write R, R pops up and you can start it. In Linux, you can open a terminal and type R and so on. So it is very intuitive, right? So you in Linux, you open a terminal and type R on the prompt, and it will give you an R environment. I have given here in this slide how to quit R. It is slightly deceptive. We would try to say Control C or quit or so, but it is quit with 2 round brackets. And this is how it goes. And help in R is very extensive. We'll be right in my second slide. I'm giving you the help features. Is because you can, as you proceed, if you have doubt with any command or doubt as to how you should do it, you use this. Either you write help and in round bracket you give the command. Yeah, for example, help plot, or these inverted commas are not necessary always. You can just write help plot in inverted commas or help plot. We'll have a look at this. Another way of getting help is put a question mark and give the command plot. Then you have help dot search and give the name, or question mark question mark. So sometimes when you try question mark histograms and it gives you an error, it will prompt you and say try question mark histograms. Okay, so uh, yeah, so before we proceed ahead, let me start with a R session, and I will share my desktop. And for the moment, yeah, so like I mentioned, you can click this start button and you say R, and it shows up R. Okay, or on the desktop you will see an icon of this kind. I have this R here, and the moment I click, it starts a R session. And here's R, and R can be used as a calculator. 23 plus 7 89, and press enter, and it gives you what it is. You say multiplication and it gives you the answer right away. If you say 2 the cap 5, it gives the exponent 2 to the power of 5. Or you can also use 2 star star 5, and that will also give you 2 raised to the power of 5. And then you have modular divisions, which we will see as we proceed. 4 percentage 3. It gives you the integer division, and so on and so forth. Okay. So then you have you have the concept of variables and constants. Like in all programming language, a variable is a location memory where its values can change. For example, I say x equal to 5. I'm assigning the value of 5 to x. Yeah, so exactly as it happens in all programming language, what is giving on the right side, that value gets assigned. It is not the equality as in mathematics, but it is an assignment operator where x, the variable x, is assigned the value 5, and now when I type x, it gives me its value. But in C, you assign values not just by using equality. Very often, the more popular way of doing it is you have the less than and a minus sign, and you assign a value. And this works exactly like equal sign. So I have assigned, this is left assignment. And now when I say X, earlier the value was 5. Now we are assigning 34. So it overwrites its earlier value and stores 34 here. Similarly, there's this right assignment. I can assign a value 28 uh, and say right arrow to some other variable y. And when I say y, I get the value of y. This right assignment is not very often used in R, though it can be used. Very often uh, uh, the less than and dash arrow is used, left assignment or equality. The most popular one is using this one to assign the values. Okay, now that we have X and Y, I can do its addition. I can do X to the power of Y and whatever. And it gives me, it can be used as a calculator. In fact, you can even store complex numbers. I can say A is 2 plus 3i, and B is, I'm assigning a value 4 plus 5i. And when I say what's the value of A, it gives me 2 plus 3i, the complex number. And say B is, oh, sorry, B, I wrongly did it. B is 4 plus 5i. Yeah, so B is 4 plus 5i. And when I say A plus B, you get the addition of these two complex numbers. You say A into B, you can do the multiplication of complex numbers and so on. Okay, then there are many other functions which you shall see as we proceed ahead. There are certain constants which are stored there. For example, we have pi, and its value is stored as 3.141593. So pi is a constant which is inbuilt there. So you can, when you have to say 2 into pi, you don't have to say into whatever divided by 360. Yeah, conversion, you can do that. Okay. Then there are certain constants like letters. If I say you have, when I write letters as capital A, B, in letters in capitals, I get A, B, C, D, and so on. It's listing all the letters there. And letters gives me the smaller ones. And then I have month names. Yeah, and uh, we can have month names and so on. And right, so we'll go back to this, and yeah, can you just have a look? Can you see the presentation? So what are the valid variable names? We have, like in all programming languages, we have some rules. It should start with a character. It can be a string of characters, and it can have a string of characters and numerics like total or capital total, capital TOTLE. These are two different variable names. R is case sensitive. Some dot find dot with dot dot, right? So this is also okay. So you can, variable name can start with a dot. It can have many string of characters separated by dots. You can also use underscores in it. This underscore is underscore acceptable. Then you can have, say, number 1. These are all valid names. The invalid variable names are, you can't put at amp, that at sound dot and at L. You can't start with the numeric one 5 then you can't start with a underscore, though you can start with a dot in your variable name, but you cannot start with an underscore. And then true, capital T, capital U, URE, all in caps is not allowed, because this is a reserved keyword. And then dot 0 any, yeah, this is not, if it was O it would be allowed, capital O, but here this character here is a 0, that's why it is not allowed. So you cannot start with a character with a numeric one. And the good practice of using variable names is use a variable name which indicates what variable it is being used for, so that it's easier for your to read your program and to um, and for readability, for somebody else uses your program, they will be easy for them to understand. So you have these numeric constants which I already gave example of. Pi is a constant, and numeric constants, you have integers, you have double precision, you have complex, and you can find out what it is by using this command type of. So for example, if I say type of A, yeah, and it says it's a complex, and type of, what are the other variables that defined earlier? X probably. It's a double, right? So this type of is a good thing where you can find out what is the type. Numeric constants which precede with these 0x and 0 capital X, they are interpreted as hexadecimal numbers. So these are, you can use hexadecimal numbers too. Character constants, you can declare certain constants as characters too. So constants are those which do not change their value during the course of the program. And while variables are ones which keep changing. So you can define these character constants by either using single quotes or with double quotes. And if you put a numeric one in double quotes, then it is treated as a character constant. Okay. So for example, say D is double inverted comma 67, and the value of D is 67. It is not the number 67. And by of uh, type of D, if you check, you'll find out that it is a character and it is not a number. And then you cannot use this D in any numeric computations. While if I had defined, if I had assigned the value of D as 67, then D is being shown as 67 without the inverted commas, which is being showed here. And now when you see the type of this variable D is, what is the type of, and it is showing it's double. Yeah. So here we are. And yeah. So then we have seen this letters, pi, month name. Yeah, I was writing month names. That's why it was giving error. When I say month name, it gives these January, February, so on. And when I use the month abs, when I use month abs, month.abb, it gives me abbreviations of these months. But these things are, though these are character constants, but their values can be changed. For example, we numeric, or these are constant. Pi is 3.14593, but we can assign some other value to pi. So be careful what has happened during the course of this. Suppose somebody writes, or you write pi is 56, then when you do pi, it will forget that the inbuilt system has stored a value 3.141593 for value of pi. From now onwards, from this stage onwards, until you log out and log back into the system, or forget the value what it is, it will remember as it as 56. It will not be pi. So use these constants, numeric or character constants, with a little bit of caution. Yeah, so it's not a good idea to rely on these. Their values can be changed, right? I can change the value to 3, 5, 56, whatever I feel like. Okay, so we have these reserved words in R. Uh, for example, I said you cannot use TRUE capital all in true as a variable name because it's a reserved word in R. So similarly, you have this list of reserved if, else, for, false, null, and any complex functions. While these have some special meaning, and hence you cannot use these. And you can find out what are these reserved words. So now I will show you how this help thing works. And when you say question mark reserved, right? And I say it opens up as you would. I will show it. It opened up the browser, and it gives you the help in that. So it shows you all the details of it. Okay, so similarly, this feature of using help is extremely good. You can say question mark um, question mark plot, and as you see, it shows plot, and it shows you generate XY plot. It shows you the description. It shows you what are the options, how do you do it, and it also gives you some kind of examples. So for example, this makes it very easy for us to learn R, because if you want to do some plots, and you can open this, and you can copy paste these lines. You can just copy these lines and paste it into your uh, into your R command prompt, and it gives you the whole thing, right? So, and then you can go into that thing line by line, and you can see what it's basically doing, what it's doing, right? So right here you can see that plot sign, comma, this command which you have here, pi to pi, right? So say, yeah, so plot, and I say sine and minus pi to 2 Oh, now the pi's value has changed, so I'll have to put it as 3.14, otherwise it will give me something else. And I plot it, and right away you are getting the plot. So what basically I was trying to indicate to you is you can use these help feature and find out. Yeah, so help can be got by this question mark reserved or help reserved. Now, for example, I say question mark. Uh, I'll just try to demonstrate that if I write histograms, yeah, it will give me an no documentation for histograms in specified package and libraries. You could try question mark histograms. So it is prompting you and saying your question mark histograms, and then the same thing happens. It opens up the whole web page. You have to have your net connected, and then you can see all these help. They are different ones, whichever you want. You can click it and see, and you can see how these are done. And down below, you also have an example of histograms, which you can cut, copy, paste, and run it here and analyze that code and see what is happening. So you see you are getting these histograms right here. So apart from this extensive help which is inbuilt in R, there are very large R communities, and on internet you can ask questions, and you can get support from the community available. And also you can also get the code specifically if you are trying to do some kind of an analysis, say clustering techniques. You can download that whole code and just adapt it to what you require to do and go ahead. Yeah. So basically what I'm trying to imply is you start using R, and as you use it, you will start use it and specifically for your problem, and do what you wish. I mean, you can get help from the net and work on it. So we have these arithmetic operators. I'll run through these fast because these are obvious and the usual ones. Addition is the plus sign, subtraction, multiplication, division, exponent. You can use this cap, or like I showed, star, which is used in Fortran, and modulus, remainder from a division, and and percentage slash percentage. Yeah. If somebody wants to ask question, they can unmute and ask, but I think there was some disturbance which was coming in. That's why I muted. Okay, so for some reason, 45 by 2, yeah. So the percentage, if you use this percentage, it gives you the modular division, right? For example, if I take 5 divided by 3, 3 goes in 5 once and 2 remains, so the answer will be 2. And the same thing, 5 divided by slash this 3, it will give you only the integer component of that. So 5, 3, it goes one time, 3 goes in 5 one time, so it gives you 1 and truncates the whole thing. Similarly, if it was a decimal number, and I say 23.67 divided by slash divided by 4, then it will give you 5 because 4 goes in 25 times and 3.67 is the remainder, and it's throwing off the remainder and it's only giving the integer value. And the same one, if I don't put the slash in between, it will give me the remainder 3.67. So these things come very handy sometimes when we are doing some loops and things. Yeah, so okay, so this is it. And the order of precedence is from left to right. And the BODMAS rules which we use, which we have learnt in school, brackets of division, multiplication, uh, addition, subtraction, and so on. Okay, so the standard rule, uh, and be careful that you put brackets right if you want the precedence of addition over multiplication. Otherwise, you'll get some other. Yeah. You have the relational operators in R. For less than is uh, just this less than sign, greater than is greater than sign, less than or equal to, greater than or equal to is two equality signs and not equal to. Uh, then you have these logical operators where exclamation mark is not, and is ampersand is and. So this element wise logical and is logical and. Usually when we are using if a condition something happened this and that happens, then you use and. And similarly, you have or and logical or, element wise or logical or. As we proceed ahead, you will see the subtlety between that. But the ones which you are familiar with most of the uh, time, we use these logical or and logical and we use and or to this pipe operator or. Then you have assignment, like we have said right in the beginning. I showed equality x equal to 5. It assigns value 5 to x, or you have the less than and this minus sign, which is left assignment, and then you have two less than and minus sign. That's also left assignment, but this is used for global assignments. Yeah. So when in the parent environment, when you are doing it, then you use this less than, and minus sign. We will come to this as we proceed ahead. As of now, just use less than and dash and this equality for left assignment. And right assignment, you have minus and greater than sign, or this global or assignment in the parent environment, you have these. So like I said, the right assignment can be used, no errors, there's no problem, but they are rarely used in R. So now this is something important. If you want to take in input from a user, say you have this your name dot name. Yeah, this is a variable name, your name dot name. You can have anything there. This is just a variable name which I am giving, which and say read line prompt enter your name, right? So for example, yeah, so you have uh, any variable name, your hmm, your dot name, okay, your name, and you are assigning this thing, and you say read line, and you give prompt. So this will give a prompt on the please enter your name, and when I close the bracket and press enter, it is giving, it's writing whatever you have asked the prompt to give you, please enter your name. And when I give my name as whatever, Hasan, and now my name is stored in that variable called your.name. And when I say your name, and it shows that it is Hasan, right? So if I run this again and I say um, some name, Avinash uh, Gupta, and when this time when I say the variable name your name, and it gives me that your name is Avinash Gupta. Okay. So similarly, you can have something else here. Suppose you have uh, another variable where I say age, and please enter your, I make the prompt go as enter your age. It will prompt and say enter your age, and Avinash Gupta will say he is 23. And when I print this, your, this is stored in your age, and when I say your age, it is 23. And now I can have a print statement which says paste, and it says inverted commas whatever hello, and inverted commas closed, and then I put your dot name, whatever variable name we had used there, and then I put another thing, you are, and your dot age, and say years old, and close these inverted commas. It will write, hello Avinash Gupta, you are 23 years old. You rerun, enter your name as whatever, say Priya, and enter the age as uh, 32, and then I run the command, it would write, hello Priya, you are 23 years old. But remember, the age at the moment is a character. So if I say type of your dot age, your age, you will notice that it is a character. So we can't do any kind of computation as your age plus one, your age plus two. So if you want, then you can convert this your dot age. You can convert it as an integer, and when I say convert as an integer, and then I put this variable, whatever that variable was, age, then your age, this type of your age has now become an integer, and now you can do uh, uh, your dot age plus 24. So after 24 years, you'll be 47 years old. Okay, so this also indicates how you can change the variable type. You can change the type of a variable by whatever you want. It could be a right? So, but this has to be done in a meaningful, careful way, uh, not messing up what is happening. Okay, so here it is. And then I will rush through these R if statement, if else statement, right? So generally, R can be run through a console prompt line by line, or we can write R scripts and run these scripts. So you can write all these uh, set of commands into a file and run it as a script file, which we'll see when we proceed ahead. Or you can run it as a bash command too. But what we are today seeing is how you run it line by line on the R prompt. And obviously it runs the first line, second, third, fourth sequentially, unless there is some kind of a statement which redirects it. It says that if something happens, do something else do this, right? So we have these if else multiple if else's which are nested, the whole ladder of it. And the if is the syntax is very similar to what we have in all programming languages, most programming languages, like in Python or in C or in. So you have if, and the test expression is in a round bracket. So these round brackets indicate that these are functions basically. And then you have these flower bracket parentheses, in which you can have one statement or a sequence of statements there. And as long as if this test expression is true, it will do all the statements within it, and then it comes out of the loop. So there can be one in this, or there can be a multiple statements. The number these it executes the whole of this parenthesis. If else is if test statement, this thing, and then you have else, and then you have the else parenthesis. So if the this test expression is true, it will do things within the first parenthesis. If not, if it is not true, then it does the else statement throughout. Similarly, we can construct an if else ladder. If test expression statement one, else if another test expression, else if, and so on. You can have if else ladder. Okay, so another interesting if else function is there. So this is something very different. Yeah, and one thing here, the indentation like you require in Python is not a must. In Python, the if statement has to be indented properly by using the tab, but in R, it doesn't really matter. So there is another this if else function. So if else, then you have a test expression and you have xy. So if this text expression is true, then it does x. Uh, Otherwise, it does y, right? So, for example, I have is equal to we have this a is equals to I'm defining a vector. I'm taking this vector and is oh sorry, my cursor's jumped off elsewhere. Yeah, so what I have is I have this. Yeah, so now we are moving on. See, we had seen how I defined A as um, I was assigning value 2 in A, and when I said A is 2, or I can define a vector. We'll come to this soon. Um, C, and then I put say 1 comma 2 comma 3 comma 5, whatever. So A becomes a vector where A is 1 2 3 5. Okay, and here if I'm giving you an example of if else if else A uh, divided by 2 is equal to 0. What I'm saying is I divide the first element of A, and if it is 0, then I say it should print it is odd. Or if it gives you if it gives 0, then obviously it should give you uh, even. And uh, if it is not 0, yeah, so if it is true, then it does the first one, else it does the second one. So when I run this thing, it says, say, I'm dividing, yeah, my A is basically 1, 2, 3, 4, 5. So when I divide 1 with 2, I get uh, a remainder 1. So this condition is not being satisfied, so it is printing odd. And in the second case, it is 2, so it is giving you even, then it is giving odd and odd, right? So now that we are with vectors, I will define, say, another vector b. And so the way of doing it is by using the C function. And in this, I specify whatever values I want to give. So I have B here. And then I can do these. I have vector A and a vector B. Vector A, sorry, vector A is 1, 2, 3, 4. Vector B is 34, 45, 67. And I can do uh, vector addition, and obviously what you have is coordinate wide. 1 plus 35, 1 plus 34 is 35, 2 plus 45, 47, and so on and so forth. Similarly, I can do multiplication with these two vectors, and it does this multiplication 1 into 34, 2 into 47, 3 into 70, and so on. And similarly, I can do division of these. So coordinate wise, it's doing division. Okay. So now, important thing to note here is, suppose I have two vectors of different lengths. For example, I have C, which has only two elements, while A has four elements. A has 1, 2, 3, 5, and C has only 1, 2, 4. And now when I do A plus C, so there should be an issue, right? There should be a problem because the addition was the first element of A was adding to first element of uh, would add to first element of C, second to second, but there's no third and fourth elements in C, while there are third and fourth element in A. So what it does is it repeats 2 4 again. So as you notice, it is 1 plus 2 is 3, 2 plus 4 is 6, and then it rewrites 2 4 again. So 2 plus 3 is 5, and 2 plus 5 plus 4 is 10. So it maps back the C values so that it fills up those values in that again. Okay. So I hope we everybody is with me, and We are moving fine. Okay, so we were here. Similarly, we have while statement. For, then you give a value in a sequence. We have for and while loops here. For a certain value in a certain sequence. So as in the sequence, as it continues, it keeps doing this loop, else it comes out. Similarly, we have while a test expression, all these in this parenthesis go on. So this PowerPoint, we will share it with you. And these are the structures which are very obvious and simple, but you can keep it handy when we are actually using them and doing things. So similarly, you have this break statement. If test expression, it will do a set of things within the parenthesis till it sees the break statement. The moment it sees a break, it comes out of the whole thing and it stops the program. So for example, here I have an example where X is, yeah, sure. This is one more way of defining our, yeah, so I had defined, um, I defined a vector by using this C function where I had given it is 1, 2, 3, 5 or 4, whatever. I can also define it using uh, one, say 23 to 34. Yeah, and you will see that X is a sequence which is 23, 24, 25, 26, and so on. Okay, so you can do it this way. And similarly, there is another way where you can define a vector by using the sequence function. For example, I can say uh, uh, C is, sorry, yeah, so my cursor is jumping from one system. Yeah. So I can define another variable, say S or some variable T, which is why I'm assigning using the sequence function, sequence, and these functions are with these round brackets, and I specify say between 20 to 100, and I pick by what is the by say 5. So it takes in steps of 5. So when I say T, it is starting with 20 and ending at 100, and we are taking steps uh, of 5 here. Similarly, I could have made it say 23, and now when I write, it goes from 20 to 100, but in steps of 23. So 20 plus 20, 43, 43 plus 23, 67, and so on. So again, your T is a vector. Okay, so yeah, so we have similarly we can define functions. Yeah, this we have seen. Now we can define functions. You give a function name and you assign function and how many arguments are in that. And in the curly brackets, you have one statement or set of statements which defines a function. For example, we have power. We are defining a function called pow. And yeah, so this is any name I am giving. I'm an assigning function which has two arguments, x and y. And this hash is a comment line. Whenever you put a hash, it will comment the whole line. And we are saying result is x to the power of y. And it's a print paste x raised to the power of y is result, right? So you can define, and whenever you run the function pow as uh, whatever, then uh, you will uh, be able to you will be able to run it. Okay, so it's a simple one. Let me not waste more time. We'll come closer to uh, how we can start doing our work. Okay, so we have seen R can be used as a calculator. We have seen some example of plot, and we have seen that basic data types are integers, real, complex, characters, logical, and so on. And we have standard arithmetic and logical operators. We have conditions and loops, which redirects these things. So now data structures in R, we have already seen you can store data in terms of vectors, either as individual variables, character, you assign name is a character, Najam or Priya or Avinash or whatever. As vectors we have seen, and these are the ways where we were storing it as A using the C function, using 2 colon 10, and you can also go from minus 3 to 3, minus 30 to 30, and so on. And okay, then you can also in a vector, you can have different things. For example, the examples which we have seen here, 1, 2, 3, 4, these are all integers. And what we are seeing here is the first element is an integer, second is a floating point number, third is a logical operator, fourth is a character one. Yeah. So you are free to define these kind of, you can define these kind of uh, vectors, which can be a mixture of different types. Then you can store data as matrices, and the form is this. A, you use the matrix command and say 1 to 9, number of rows 3, number of columns 3, or whatever, number of columns 2, number of columns 5, or whatever you have, and then it fills up, and you will see that fills up row wise. We'll just run it and see. So it uses the convention this way, and otherwise you can say by row. Yeah. So what I mean here is what we'll do it here and have a look at it. Yeah. So before we come to that, we have this vector A, which is 1, 2, 3, 4. And if I say vector and square brackets and I give say 4 in that, so this will return me the fourth element in the vector A, right? So if my vector T was, yeah, so for example, T, and when I say third element, it will give me this third element in T. Yeah, my T, if you see, is 20, 43, 66. And when I say T, 3, it will give me the third element, 4, fourth element, and so on. So this is how you can get whichever element which you want. And now suppose I want to define a matrix M, and sorry, um, M, and I say matrix, and I say, for simplicity, I'll just run this, and uh, rows, number of rows is 3, and number of calls is 3, and number of number of number of, not rows, row is 3 and number of calls is 3. And when I say M, you see it is filling, it is 1 to 9, but it is filling up row wise, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So similarly, if my matrix was, say, 10 to 19, and I give it some other matrix number, and it is filling up these values. Yeah, it is giving you a warning that it is overshooting 10 to 19. There are 19 elements, but all the same, it made a matrix up to 18th. Yeah, it filled up 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. So this is the convention which it uses by default. But suppose you want the matrix to be filling in column wise. I want 10, 11, 12 is the first row, and 12, 13, 14 as the, yeah, 10, 11, 12 is the first row, 13, 14 is the second row. Then you have to specify in this, by row. Yeah, by row equal to true. So when you say this, and when I look at M2 now, then it has filled in the first row, 10, 11, 12, 13, 14, 15, and 16, 17, 18. Okay, so this is it. And similarly, suppose I have another way of constructing matrix is, suppose I have a matrix C, which is 1, 2, 3, 4, 5, 6, suppose. And I have a vector which is this, and I say dimension of X is C 2, 3. So now X becomes a matrix which has 2 rows and 3 columns, right? So this is one more way of making our matrices. And now we look at the list. So list is, you can again use this list command to create a list where you can it can be of different data types. You have A, which is 2.5. Character A is 2.5, B is true, and C is a vector. Okay. Now, important one which we see here is data frames. Most of the tables which we have, astronomical tables and so on, they are stored as data frames. So data frames is, for example, are many lists which are stacked up. So you may have many columns, and first column can be, say, a serial number. Second column can be a numeric data, which is, say, age. third column can be a character one, which is name of a uh, of of a, of a person, and third can be some kind of a factor where male or female it is true or false, or it's yes or no, 0 and 1, and so on, right? So we have these data tables where we have names of serial numbers on that, then we have names of, say, galaxy names, then you have their RA, and you have depth, and you have their log in ages, and you have distance from the galactic center, and so on. So these are basically data frames where you can stack up many lists as one, and you use these read table and read.svs functions to read uh, uh, data from these tables or these from data frames. And this, as you see, this read.csv is read if it's a comma separated variable. Okay, so now let's come back to this and look to our R console, and just to show you an illustration. Uh, if I say n is a vector, where I say n is floor of r norm, and I say 10,000 values with 500 comma 100. Yeah, I'll just run this, and then I will tell you what each thing stands for. uh, r norm, there should be two brackets here. One is for floor, other one is this. Then I save it in T, and I call it a table, and I'm saving values of what I have stayed in this table. And when I say do a bar plot, this is just to show how uh, flexible R is to do it. And here you are having a bar plot of this thing. Yeah. So what have we done? We'll analyze this uh, type one by one. This R norm, it is creating a random table of values, and yeah, so R norm is a function. R norm is a function where we specify how many values we need. We right? We want 5,000 values whose mean is say 300 and standard deviation is 50. Right? So R norm will create this one, and let me say store it into some variable called x. So if I look at x, it is giving me all these values where they are all in an normal distribution. When we are running this, when I am doing a floor of this, when I do a floor of R norm, and let me save it into, say, some other variable called xf. So basically, floor, it will truncate all the, it will just keep the integer value, right? So it is giving all those values which you had seen in x, but it is getting rid of all the dot 467, 4655, and it is just keeping the integer values. And when I'm using this command uh, t table n, yeah, when I'm for now I'll do it with my new variable which was xf. It is making a table. So it is taking these random values which it has taken, and it is counting how many times each one has appeared and making a table out of it. For example, 356 has appeared 29 times. 4186 has come 4 times, 417 has come 4 times, and so on, and 228 has come. Yeah, so it's a table which it has made, but since the table is too big, we are unable to see it here. Maybe we can run the same thing with the smaller number of and then when finally I do the bar plot of this t, then I'm getting the bar plot of, yeah. So you are seeing it's a normal distribution, and it has randomly created some values, and I specified I needed 5,000 values where the mean should be at a certain point. So the mean is sitting here, and the variance I said should be 50. So you have a look at this. My yeah, so 5,000 values. My mean was 300, and my variance was 50. So you can create normal distributions, and we'll come to there are various statistical distributions which are stored in R, which can be used here. Okay, so uh, this is what we have, and uh, okay, so now we'll proceed a little further ahead, and you notice that you needn't run all of these in 3 different lines. R is very flexible. You can run all of them in a single line and say bar plot table floor R norm from 10,000 to 500 R. X lab, X label is numbers, Y label is frequencies or whatever, and then it will construct the way you want it to. Okay. So, here it is. Now, one important thing which you will be required as you proceed is you have installed your basic R in your system, but there are various packages which are there which you need to install for certain functions, things to run. For example, you have this package called ggb pub-r, and to install it from CRAN. You can have a look how to install packages in R. But yeah, so there are various ways you can use git install to install that, or you can use install.packages, for example, from CRAN. Say, so how do you do it? You just have to run this command from your R prompt, install dot packages, and you have to specify what is the package name. For example, ggpubr, right? This is a package which does a lot of statistical things and graphical things. So when I run this thing, it opens up uh, the CRAN mirror sites, and you can choose whichever you want: Australia, Canberra, Melbourne, China, Hong Kong, Ecuador. So whichever you expect to be a country which is may have a good server, or it may be night time for them, whatever, you can choose whichever, and you say okay, and then it will start installing the whole thing, and it is installing the packages, and the binary packages are installed in this location it has shown. So it has installed it, ggpubr, a success package, and MD5 sum check. Yeah, so it installed it and checked the thing, and it has said it has downloaded it well. Now, if you want to use this, uh, then if you want to use a certain library, you say library, and you specify in inverted commas whichever this gg pub r, this library I want to use, and right, then all the functions and things which are package one, gpub, where R was built under R version this thing, and ggplot2 was built under, yeah, it has installed it and it has loaded this package. Okay, and with using these packages I can do my uh, work. Okay, so now we look at one last example, and so now when we have say statistical your data, astronomical data or whatever, and suppose you have a big database in which you have various columns and rows are different objects, all different galaxies or different clusters, and in columns you have their locations, they have ages, you have their RA deck and uh, ages and metallicity, and you want to find correlations between any two columns. So correlation is there are different ways of to perform correlation. We have Pearson's correlation, we have Kendall-Tau method, you have Spearman's row correlation. And I will just show you Pearson's one. In fact, it is very easy to do the other ones too. But since we are uh, running out of time, so basically, if you have two variables and you want to see whether there's any relationship between them or not. So one way is you can plot that data, and by plotting it, it will give you what the scatter plot itself gives you some indication whether it is correlated. For example, the one which you see here, you see a positive correlation. As x changes, increases, y also increases. So these are positively correlated. While if there is no relationship between them, the scatter is the total scatter. You can't see any kind of a trend. Your x's may increase for the same x. You have different y's for different. Okay, so there is no such relationship, and there can be a negative correlation. As x increases, y is decreasing. So the scatter plot right away is indicating this kind of a thing. And then you very often want to fit a line, a regression line, which tells you, it gives you a line, a relation between x and y in terms of a function, which will tell you how y is related to x in a functional form. Okay, so and from the value of the correlation coefficient which you get, you will say how much of relationship there is between them. So this correlation lies between -1 to +1. +1 indicating they are highly correlated, which shows that as x increases, y increases. For example, I have say measurements. I take a wire and for different lengths I measure the resistance, and I see that as the length increases, the resistance increases. Yeah, so if you do this experiments and tabulate it, and you try to find a relationship between them, you will find a positive correlation. But in certain things, you may not find any relationships. For example, the number of goals scored in football to the height of a football player, you'll see that there is no correlation. A very tall person can also be a good goal scorer, and a short man can also be. You have Ronaldinho scoring a lot of scores, you have Maradona scoring, right? So there is no correlation, and you would get some kind of somewhere near zero if you try to measure performance. Yeah, whether you height and weight, tall people are heavier, or metallicity and location in the galaxy. You are trying to find a relationship between them. So whether you get a positive correlation, no correlation, and if you get somewhere minus 0.97, 0.987, then it shows they are highly negatively correlated. So as one increases, the other decreases. Okay, so this Pearson's correlation is a parametric one, while Kendall, Tau, and Spearman's is a non-parametric one. This we shall get into what are parametric tests, non-parametric ones as we get into this. And so Pearson's correlation measures a linear dependence between two variables x and y, and also known as a parametric correlation test because it depends on the distribution of the data. It can be used only when x and y they form a normal distribution, and the plot of y equal to fx is a named after the linear regression curve. Okay, so this is the formula. You find the mean of x. Here you have x and you have y. You find the mean of x, you find mean of y. Then individual values you subtract from each one in the table, x minus its mean, x1 minus its mean, x2 minus its mean, and so on. Similarly, y from the y's mean, and then you take the product of it and then take a sum of it, and you divide it by the root of the squares of the two root of it, and you get the R value, which you plug it into this t test, and n gives you the degrees of freedom. So if your number of n minus a gives you the degrees of freedom, and it happens to be n minus 2. N is the number of data points you have. So if the data has 5,000 values, then it is 5,000 minus n. And then you look at the value of this t, and you compare it with the table value. And then you, so you have this R1 thing which gives you what is the correlation. So right from there you can find out whether they are highly correlated or not, or and so on. Okay. So in R you have these kind of functions, correlation x comma y, and you say method equal to Pearson's or Kendall or Spearman's, and it will do the test. Or you say correlation test xy and which method you are using, and it gives you the values. The one which I will share you, I will show you how to even read data. Say suppose I am reading a delimiter file. So you have a file, read data delimiter file.choose, or read.cbs file.choose, and you store it in this my data. And as an example, I will run this one and show you. So, and then we can run these. We can run these commands. Okay. So, yeah. So now if I say, I'll run this command on this prompt, and I say my data, and I'm storing in read.cbs, and I'm asking file.choose. So it has opened this box, and from this I have to choose which data I am looking for. So my data file is say data.txt, and now when I say my underscore data, whatever name you want to give, and you see there's a text data file which I have created and stored in a certain location. I can, and it has X and Y, two columns, 1, 3, 2, 4, 3, 5, 4, 6, and so on. And now I want to uh, run this correlation. And I want to run my correlation. And I run this command here, and I say correlation x comma y and method equal to, and I say Pearson. Okay. Yeah, you have to read this values. He doesn't know what these x and y's are. So uh, you have to, yeah, so basically we'll have to, I'll have to specify what my x is. Just a minute. So if I do this thing, my problem is coming here. In yeah, my x, I have to use my x data. Yeah, I have to read my x and y data this way. See, this scatter, my data is x equal to my file x equal to x. Why is this? Add regression line and file, and when I run it, it is running. Yeah, just a minute. There's a question here. So see, here is my data and this is how it is plotting. Okay, so the data which I have in my file is highly correlated and it is fitting in the line perfectly well. So the one which it failed here is because I didn't specify where my data is. Yeah, my data is read file this, and when I'm reading this file, I have to specify which are the which is being x is being read as this and what is my y is being read as, and then it will give me a proper one. Okay, so um, so similarly uh, we can run other ones. For example, there are certain databases which are there inbuilt into R, and say if I take cars underscore data and I'm storing in this uh, empty cars. There is a database which comes with R, and now if I say head and I look at cars underscore data and say 6 of these, I'm looking at the header information. Yeah, so this is my table, and then yeah, I've already loaded this thing, and now for my regression curve, Control C, and when I do run my GS scatter cars data with X as the MPGs, my Y as the weights, whichever column I have. So this is how it specifies which column you are reading and what is the and then confidence level true, and then when we uh, say correlation current true and you fit it, you set the X label and Y label, and it gives you what is the R value, what is the coefficient value, and so on. So similarly, instead of Pearson's, if you change Pearson's to Spearman's, or Kendall, then it will do the other correlations. Okay, so with this we will with this we will end our thing, and yeah, so let me see the questions. There is a question which we can we draw a curve, say Gaussian curve in our plot? Yeah, you can draw the curves. Yes, you have these Gaussian functions which are stored there, and then you can draw those and you can overplot. You can have, so in the next session we will look at plotting in details, where you are plotting, say, data, and along that you are putting a Gaussian curve in that, so that it shows you how the data is deviating more from. How to read fits file in R. Yeah, so one possible thing is you can there are these tools with which you can convert uh, fits file into CSVs and so on, and you can read the CSVs, or we can just Google search and see whether you can read fits files in R. So R documentation. Yeah, so this is the command, read fits file into do. Yeah, so as I mentioned, you can just Google search and right away it says read fits file equal to the name of the file and how many lines you want to maximum read. Yeah, fits header, if it's none or it is remove or substitute, whether you want to substitute it, whether you want to read it. And this kind of a read thing holds for all, whether you want to read the headers, you want to remove them, and so on. So this is how you can. Okay. So so how do we access elements of a matrix? So in the same way as you were matrices here, what were the matrices I defined? S was a matrix, or yeah, maybe M was a matrix. Yeah, so just a minute. I'll open this thing. M was a matrix. So if I say square bracket and I say 2 comma 3, it will give me the second row and third column. 8. Similarly, if I want the first element, I say M 1 column, second column, right? So that's how you can get the fourth element. If I don't specify the first one, I say comma 2, then it will give you the whole of the second column. Yeah, 4, 5, 6. And similarly, if I specify, I don't specify this, but I specify, say, the third row, it gives you 3, 5, 6, 9. Yeah, you can access CSV and fits from the URL. You can do that. Yes. So no problem. We'll see examples of that. so you'll have to know the whole path of that. I had some more data here, astronomical data. For example, uh, where is my, yeah, so we have R file, and we have these long data in CSV. Yes, so I downloaded this too. Yeah, so this is uh, from from 2 mass data, and we can read, say, log ages by distance, find whether there's correlation, EB minus V versus metallicity and various things. So we will deal with more databases and astronomical databases in our next session. So yeah, you can specify the whole path there from where to fetch it. You have to have a running database to do it. So you can try it, but in the next session we will do it. Okay, so uh, yes, for 6 IT and for 6 CT. Priyam asked, while using R, I came across POS6 IT and POS6 CT. I would know the difference well, but probably it has to do with the see Linux was, when it was being developed, it was developed in various. Uh, it started off in Bell Laboratories, and then it went to various universities, MIT and other places, where they developed different versions of Unix. So you had those certain nuances in kernels, and uh, and then Linux was built by Linus Torvalds, where he tried it. So most of the Unix which was built was fixed to the architecture. The DEC Alpha systems had their own Unix, which ran only on that. Sun Machine had the Solaris, which run on those. So Linux was an attempt to have it on Intel type of systems, where Linus Torvalds uh, put some questions on that. So there are different threads of that POS6, and so I'll have a look at it, but it has to do with some such small nuances of that. Okay, so I'm sorry I can't answer you well now. Maybe by the next one next session I'll clarify that. Yeah, one thing is to uh, search for that and do it. Okay, Priyam, I'll handle that in the next class. Okay, yeah. Okay then. So for today we'll end. So try to run R. Try to create small data files um, and read them. Read different columns of it into it and see how you read into that, and then how to. Yeah, so first play around with small files which you meet, so that you know that what you are reading and writing it on the terminal is actually showing what you are doing. Otherwise, if you just do it with some databases and directly do it for uh, big databases on the net, you'll be just doing it as a black box. So first get used to these simple commands of reading files, reading variables, reading this, reading lines and writing it and dumping it into files, and then proceed ahead. Okay, so let's end with it